SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. So last class we closed the topic of receptance. Now this class I thought I will present some ideas about damping. Okay. Damping is a complicated phenomenon or a complex phenomenon. Let me tell you that this particular course which I am teaching, I myself learnt it from Professor Sodell. And when it came to this section on damping, he said that he came to study mechanics with the intent of figuring out damping, okay, what this phenomenon is. And then towards the end he kind of concluded that it's a very complicated phenomenon, you cannot really nail it down, okay. Yet it's part of all dynamical systems, okay, and we deal with it using experiments, taking support from experiments and figuring out some empirical values. So I will put some thoughts together, okay, because even in pure analytics you have to include some damping for meaningful results, okay. Now damping comes from many different directions, and you can have it coming from fluid viscosity, okay. As you move in a high speed car you will have wind blowing against you, so okay, there's kind of a drag, okay, that will take out energy from your mechanical system, okay. And energy can be taken out at joints, okay. When you have joints in a system you can have energy taken out, okay. And you can have energy taken out from within the material, okay. Here itself there can be a nonlinear component where the damping is kind of proportional to velocity square, or in the normal way proportional to velocity. Now there is damping within the material, which is, we call it either internal damping or we call it hysteretic damping, okay, hysteretic damping. So you have many sources of damping, okay. The boundary conditions may not be very strict, okay. Boundary is not strictly clamped or supported, so boundary leaks into the neighbor, into the neighboring material. Okay. So if a cantilever is not strictly clamped over here, and there is the energy flow into the wall. Okay. So there's many ways that damping occurs. Now if you do a model test, okay, if you take if you take a plate, suppose a simply supported plate, and you hit it with a hammer, okay, you hit it with a hammer and you measure it with an accelerometer, okay, then you will see this in your frequency response function. You will see this sort of graphs, okay, plotted on a log scale. This is a frequency response function. And then these are your resonances. These peaks are your resonances, okay, and the peak value and the way it rises, this region is damping dominated. This region around the peak is dominated by damping, okay. So what we do is find the modal damping coefficient. Modal damping coefficient. Typically we do this half power point method. Okay, to figure this zeta k or zeta mn. Okay, so now, I mean, given that the nature of damping is very complicated, it comes from many sources and it changes with boundary conditions, it changes with temperature, it changes with dimensions of your system, okay. So given that, we will put some sense into how this internal damping, which is signified by a loss factor, eta is a loss factor, eta is typically used to denote a loss factor, whereas zeta k is typically used to denote modal damping coefficient. And in the text, lambda has been used as the equivalent viscous damping coefficient. Viscous damping coefficient. Okay. So we'll connect these three. Okay. This is nowhere an exhaustive presentation of damping, but we need to know something. So we'll do that here. We'll connect the three. Okay. So in the forced response, when we looked at the forced response, we used the damping term as lambda times u I dot. Okay. So this is the equivalent viscous damping coefficient. And there is a velocity in the ith direction. Okay. So some fluid, and fluid behavior is taking out the energy from your vibrating system. Okay. And it is proportional to lambda times the velocity in each of the directions. That is the idea. And we are looking at harmonic motion. We are looking at harmonic motion. Okay. Then ui is equal to some capital ui sin omega t. This is the displacement in the ith direction. I is 1, 2, 3. Okay. So alpha 1, alpha 2, alpha 3, back to square 1. Okay. Then what is the force? Force in the ith direction is lambda times the velocity, the derivative of this. So which is omega ui cos omega t. Okay. So what now is the average dissipated energy per unit surface area and per cycle, or in one cycle of vibration, because it is harmonic at omega. Okay. So we denote by ED the energy dissipated. This is per unit surface area. So we have the area integral. Okay. We sum in the three directions. Okay. And integrate over one cycle time period, then lambda and force into velocity. Okay. Force into velocity is power integrated over time is work. Okay. So lambda, so we will have a squaring of this quantity. Okay. So ui square omega square cos square omega t integral over time, integral over surface area. A is surface area of the shell. Okay. So if we carry this out, okay, so what we will get is that this will give you a half. Okay. So that gets me lambda pi, okay, omega 1 over A integral over the surface area. Okay. U1 square plus U2 square plus U3 square. Okay. See, this gives me 1/2 minus cos 2 omega t. Cos 2 omega t integrated goes to 0. So I have a 1/2 integrated over time. That gives me 2 pi by omega into half, which is pi by omega. So pi by omega takes out 1 omega. So I get pi lambda omega in front and an omega A in the denominator. And this area integral over area. Okay. Okay. So now what is this equivalent viscous damping coefficient? What is that? That is lambda is equal to ED into A divided by pi omega integral over area U1 square plus U2 square plus U3 square dA. Okay. Now in the kind of structures we are seeing, we are looking at thin structures. We should not forget we are in the thin plates and shells topic, and hence largely it's transverse motion or U3 motion. U3 motion. So that U1 and U2 are much smaller than U3. So we can drop this. Okay. So in many common cases this is given by EDA by pi omega integral U3 square dA. Okay. So now that's as far as what this lambda means. Okay, viscous damping, how we arrive at it, or what is the definition of lambda. Okay, now we look at internal damping. Or hysteretic damping. Okay, so that is what that is, that if you take a longitudinal specimen, okay, you take a longitudinal specimen and substitute, I mean, have it go through, subject it to oscillatory forces. Okay, what will happen is that the force and the displacement, will not be always a straight line falling on top of each other. It will acquire a width. Okay, it will acquire a width. Where this area of this now elliptic region is the energy lost. In internal damping. Okay, so this area is equal to energy dissipated per cycle and volume. Okay. Now, if we divide the force is divided by the area or cross sectional area of the specimen, and displacement divided by the length of the specimen. Okay, then we get a stress strain curve which looks similar. We get a stress strain curve, and that also looks like the same what we drew before. Okay. Now, if we put this in terms of equations, and try to put in a model, develop a model which reproduces this behavior mathematically. Okay. So, to start with, we have sigma, this is a 1D specimen. So, sigma is E times epsilon for a rod. Okay. Then sigma, okay, we can say is some sigma max, and let us say it is oscillating at sin omega t, it is being oscillated at sin omega t. And what is this sigma max? Sigma max is the max force by area of the specimen. Okay. So, what is it now in terms of strain epsilon? It is sigma max divided by E sin omega t. Okay. Now this is what our Hooke's law or so suggests. Okay, but this gives graphically a straight line curve, a straight line curve. Okay, so it won't give this region in, this bulged region, elliptic region. It won't give. It will give a straight line. It will give a straight line as you oscillate. Okay, so now we have to develop a model. We have to develop a model. So what is that? Develop a model. Develop a model. Okay, so what is that? What we do is we take epsilon, we take sigma max sine omega t, and we bring in a modulus which is complex. The Young modulus is now complex. Okay. So as a result, what happens now? As a result, is in the complex form. As a result, we get sigma max. If we convert the denominator into magnitude, we get E square root of 1 plus eta square sine omega t minus a phi. And what is phi? Phi is tan inverse eta. Okay, and it is known that eta is typically small. Eta is small. Okay, so what happens is phi is approximately equal to eta. Okay, so that square root of 1 plus eta square is taken as 1, in which case epsilon turns out to be sigma max over E sine omega t minus eta. Okay. So what this now says is that sigma and epsilon are not in phase. Not in phase. Okay. So now what we get over here is we will get an ellipse now. Okay, we will get an elliptic shape. So if we plot it, it come out so well. Okay. So then this is your half major axis. This is your half major axis, and this happens to be your half minor axis. The half minor axis. Then this is your maximum sigma max. Okay, and this happens to be epsilon max. and this portion is your sigma max by E eta. Okay, and this angle is alpha. This angle is alpha. Okay. Now, what is the major axis? Half major axis will be sigma max over cos alpha. Okay, and the half minor axis is sigma max by E eta cos alpha. Okay, and what is the area dissipated, energy dissipated? Now we said was equal to the area, okay, of the ellipse, and it is energy dissipated per cycle and per volume okay, that is the area of the ellipse, and what is the area ellipse is pi AB, pi times A times B, which is equal to pi times sigma max by cos alpha into sigma max by E eta cos alpha, which is equal to pi by E sigma square max eta or pi E epsilon square max eta. This is E1. Okay, don't confuse this E1 and this E. This is modulus. Okay. So this is per unit volume. So total in the volume, total dissipated in the volume is length into breadth into h into this with quantity pi E epsilon square max eta. Okay. Now, maximum strain energy, this is what is lost. This is what is lost. Okay. So, what is the maximum strain energy? In the test specimen? Okay, what is the U max? You have seen this when we did Hamilton's law, which is 1/2 epsilon max. This was per unit volume, so into LBH. Okay, so this is LBH, the volume, half E epsilon max squared. Okay, so now what is eta? Okay, so eta now turns out to be 1 by twice pi Et by Umax. Okay, so if we bring in connect these two, we connect these two. Okay, so Umax is LBH by 2 into E epsilon max square. We connect, substitute Umax in here, then what we get is eta is equal to this. Okay, the loss factor. Okay, so the dissipated energy is twice pi eta times the Umax per unit cycle. Okay, so for the case of a shell also, so this is a 1D specimen, for a case of a shell also we will extrapolate and say is twice pi eta Umax. Okay, Umax is strain energy in the shell, peak strain energy in the shell. Okay, then the energy dissipated, so we have Et, okay, is equal to twice pi eta Umax. Okay, if you want to do it per unit cycle, per unit surface area, per unit cycle, per cycle, per surface area, then we divide from here to here by surface area. So we get twice pi eta U max by A. Okay, so now the equivalent viscous damping coefficient what did we do earlier? This, right, EdA by pi omega, that EdA by pi omega. So EdA by pi omega integral area U1 square plus U2 square plus U3 square dA. Okay, so now that was equal to lambda. Okay, so now EdA is twice pi eta Umax, okay, divided by pi omega integral area, this term here, okay, that is equal to lambda. Okay, so if we take this out, so this is how lambda and eta connect. Okay, this is how the equivalent viscous damping coefficient and the loss factor they connect. Okay, now if we remember Rayleigh's method, we remember Rayleigh's method, Rayleigh quotient. What was it? Omega k square was u max by rho h by 2 integral u1 square plus u2 square plus u3 square dA. Okay. So now what we have here is that from these two, from this and this, we can connect eta and lambda, okay, and omega k. So that becomes equal to lambda is equal to rho h, okay, omega k square by omega into eta. Okay. Okay, lambda by eta into omega, lambda by eta into omega is this quantity. Okay, lambda by eta into omega is equal to this quantity. That is also equal to omega square k by rho h, omega square k by rho h. Okay, sorry, omega square k rho h, my omega square k into rho h. Okay, lambda divided by eta into omega over here is this twice u max by this integral. Okay, so that is equal to omega square k rho h if we bring 2 up here. So this is the connection, is also a connection. Okay. Now in the how to connect this to the modal damping coefficient. Okay, so we did it using viscous damping coefficient. So if we bring in the loss factor, through the complex modulus, okay, so what now we get is in the equation of motion, we get 1 plus j eta Li u small u1 u2 u3 minus rho h ui double dot is equal to minus qi star e to the power j omega t. Okay, I think we are running out of time, so I'll just stop the lecture here and continue from the next class. Thank you.